Hello and welcome to the 16th episode of the Business Intelligence Report, a Bright Talk original series where every month we're exploring how businesses can realise the transformative power of data. In today's webinar, we'll be taking a deeper look into machine learning solutions, in particular data-centric machine learning and machine learning pipelines. My name's Eric Topham. I'm the CEO of a machine learning innovation company called TDAB based in London. And today I'm very lucky to be joined by Rajdeep and Nick, who are hopefully going to introduce themselves right now. Rajdeep, do you want to introduce yourself first?
Yeah, absolutely. Thanks for that, Eric. Glad to be here. Good morning and good evening, based on where you are. This is Rajdeep Biswas. I'm a director of data and AI here at Microsoft, and my charter works with Microsoft's customers in their journey from conception to the actual productionalization of data and advanced analytics workload. Great to be here.
Excellent stuff. Thank you very much. And Nick, do you want to introduce yourself quickly for everyone?
Yeah, thanks for having me here as well. I'm the director of, in the past I was the director of AI at Gixter. Like Rajdeep, I was responsible for the entire AI practice and end-to-end machine learning solutions delivery for strategic accounts like Canon, Denso, Vodafone, JSK, and other notable brands. And currently, I'm CEO and co-founder of Metapixel AI. We do visual content production for e-commerce, trying to automate routine processes in that workflow.
Excellent stuff. Well, I think I'm really excited to have the two of you here. I think we've got a lot in common in terms of our interests, in terms of ML and how we productionize and industrialize it. So we'll get stuck into that in a second. But just before we get really started, I do just want to remind the audience that we are live and interactive. We want to hear your questions and your feedback. So please do submit those through the player any time, and we'll do our best to weave those into today's discussion. So without further ado, let's get started. So I think we'll sort of warm up with a few, starters for 10. Very, very basic one to start with, which I'm going to pitch in no particular order to Rajdeep first. What is machine learning? How would you define it? And could you help the audience understand what the difference is, if there is any, with fields such as deep learning that they might have heard about?
Yeah, no, absolutely. Thanks for that. I think there are many definitions of machine learning that floats around, but really the one that sticks and speaks to me is machine learning, as we know, is an application of artificial intelligence, which is a broader term encompassing machine learning, deep learning, and whatnot, and that includes algorithms that parses the data, learns from the data, and then apply what they have learned to make informed decision. So that, to me, is what is machine learning, right? And there are hundreds of examples of machine learning. I mean, for example, on-demand music streaming service, right? For the service to make a decision about which new song or artist to recommend to a listener, machine learning algorithms associate the listener's preference with other listeners who have similar musical taste, right? This technique, which is often simply touted as AI, are used in many services that offer automated recommendation, right? Now, more specifically, I would say deep learning is considered an evolution of machine learning, and it uses programmable neural networks that enables machines to make accurate decision without the help of humans. So it's more sophisticated on that regard. I would also like to bring a quote from Andrew Ng, the chief scientist of Baidu. I mean, whoever is in the field of machine learning knows Andrew. He says that AI is very similar to a rocket ship, right? You need a huge engine and a lot of fuel. And if you have a large engine and a tiny amount of fuel, you won't make it to the orbit. And similarly, if you have a tiny engine and a lot of fuel, you won't even take off. So the analogy to deep learning is that the rocket engine is the deep learning models, and the fuel is the huge amounts of data that these models feed on.
Cool, excellent. Well, I think that's a great way of explaining it to to a large part of the audience for whom this is probably quite mystifying. And personally, you see so many sort of people trying to define what machine learning is. I think one of the nicest ways to think about it is the ability to effectively program a computer through the application of algorithms, so that you're not applying hard-coded rules, right? So a computerized machine can learn from associations of distributions fundamentally in data. Nick, in terms of the place of machine learning within sort of modern analytics, where does it fit into you as that within that sort of very broad field? And sort of, could you kind of explain for people how machine learning has developed over its long history, much longer than perhaps Udemy, for instance, might make you believe that it has been around for? How has it evolved over the years and more recently in particular?
Yeah. First, I just want to say kudos to Raj for bringing this analogy with the rocket ship. This is first time I hear it. And I think it's beautiful, just like very, very good metaphor of explaining what is a combination of algorithm and data makes together. So going back to the question you, Eric, asked about machine learning and the place of machine learning in the entire analytics landscape, I like to think about it on a spectrum from the most simple automation that you could do using simple rules to the most sophisticated type of automation or cognitive strong AI, or think of it as Turing test as one potential way to qualify the system as like very smart. So on that spectrum, from very basic rule-based automation to strong AI, which essentially is equivalent to human brain, you could have a place for machine learning. And I would say it's where the complexity of the problem is big enough that you already cannot maintain it in your memory. You cannot maintain it or hard-coded in rules. What you could do is to take a lot of data, pass it through the algorithm, and make sure that the coefficients, the parameters in the machine learning model capture the statistics in the data and different dependencies between the features and the target variable, so that then it could be used in making new predictions. So from that point of view, I would say it's one of possible techniques to achieve automation. And in particular, it's a technique that allows us to do more complex types of automations compared to what was available before with simple rules and standard programming languages or paradigms. In terms of evolution, the first notable place in the history of AI was Rosenblatt paper about perceptron, right? This is like an implementation of a single neuron mechanism where you could pass data through it, and then it will learn a way to separate points in a two-dimensional space, for example, right? You have points from one class, points from the other class, and the goal is to make a line that will separate them out. And there was a proof that with sufficient number of samples coming from the same distribution, we could actually use the perceptron algorithm to draw that line. That was the beginning of AI, machine learning. Then the term got rebranded multiple times. It was pattern recognition or decision trees like in 70s and 80s. Then it became neural networks. And then because, as Raj said, we didn't have enough fuel at that time, we could create a very complex rocket, but we didn't have enough fuel and we didn't have enough compute to make it work. So neural network, there was like so-called winter, 1980, 1990, where people thought, cool, neural networks are very interesting from the modeling perspective. And actually they are universal approximators for different functions. But we didn't have some things to make them actually work. The community shifted to statistical-based machine learning and the application of learning-based algorithms coming from statistical principles, probability theory, and so on. And then in 2012, there was a breakthrough. First time in the history of humankind, neural network-based algorithm was able to beat the algorithm for computer vision based on, let's say, alternative approaches, right? Like morphology analysis, different filters, and so on. So essentially, deep learning surpassed traditional computer vision for the task of tagging images. And then I think a few years later, computer vision based deep learning algorithm actually surpassed humans, or it became comparable with humans in the task of making images tag. And all after that, it's just history. Like we started seeing like speech detection systems, speech synthesis systems in 2020, like BERT, GPT-2, GPT-3, and all of those evolutions. And now recently, I think the most exciting application in 2021 was in May, June 2021, OpenAI released Codex. Essentially, you could speak to the computer and computer will write programs for you. So that's basically how I see the evolution of the field and what is the role of machine learning in the entire automation landscape.
Great. I think that's a super overview for everyone. And I think that in a sense, this laying out this evolutionary history should in a way help people understand that, in fact, it's probably unhelpful to try and classify definitions of what machine learning is, because in fact, there has been a kind of a confluence of different techniques, methodologies from different fields, right? Back when I was doing my PhD, I did a lot of what was called statistical learning, which was effectively machine learning, but because I was in the biological sciences, there was a different name in that field. So I think there's been a lot of sort of influence from different areas that has contributed, and a lot of statistical modeling. You would do a Udemy course and you would get told that was machine learning. So I think that I can completely see where the confusion is for people. But I think laying out this kind of history like that is really helpful for people. So we shouldn't linger too long, I think, perhaps on definitions, because what we really want to get to is, where the state of the field is and how do we actually, scale these systems, and what are the roles of these things that people might have heard of in terms of, machine learning pipelines and data-centric machine learning. So in terms of, regardless of industry and handling those increasing amounts of data, is there a need for more data-centric approaches to machine learning as we generate these increasingly large volumes of data, or should the discipline really focus around the optimization of models, or what people might call model-centric machine learning? Rajdeep, what's your view on this kind of emerging discussion in the field?
Yeah, I think that's a very great question. And firstly, kudos to Dr. Nick. He was spot on about how we are achieving parity with humans, and really machine learning is all about extending and complementing human capabilities, right, as it continues its evolution. Now, coming back to your question, yes, the question itself is relative, right? And let me take a different approach for answering this question. I think there is a very distinct shift that I am observing, being both from the field of data as well as machine learning, is a marriage or a merge is happening between traditional data warehouse, unstructured data, and machine learning. For example, right now you can query in Azure Synapse, which is the evolution of SQL data warehouse. You can use a machine learning model natively in SQL, and that's huge, right? And that just speaks to me that data-centric and model-centric machine learning, these are not separate things. It needs to walk together, right? And so that's where I'm coming from, because you can build models and you can build heavy deep learning models, but to custom tune it, you still need data, right? Another color to this is when someone is using the commercial machine learning models. I think, for example, in Microsoft, we expose it as cognitive services. So those are pre-built models that we build, not using customers' data, but using our data, and then customers can use their own data to train it. So one thing is for sure, all the cloud companies and the commercial, the SaaS offerings of machine learning models, what they're doing is they're trying to minimize the need of this huge amount of data that you need for a custom machine learning, right? So that's what we are trying to do. However, as of today, data is still very much needed, and data should be the spearhead of how we are trying to solve the business problem and make informed decisions.
Yeah, I think what I'm trying to drive at a little bit is that I know that recently there's been some research that's been published where there have been benchmark tests done to try and look at the degree of model performance uplift that you get, whether you focus on a strategy to improve the quality of the data that's then used to train the model, or whether you focus on a strategy of optimization of the model or the model architecture and hyperparameters itself. And what you find is that, well, at least in these pieces of research, you get an order of magnitude greater performance uplift if you take the data-centric strategy. And of course, one of the other criticisms of deep learning is that it's very febrile and it requires large amounts of data to get performance uplifts over more traditional approaches. So I think that's kind of where I'm sort of driving at with the question. I mean, Nick, as somebody that works in the computer vision space, you're obviously relying heavily on some of the latest developments in deep learning to do that. So what's your view on this kind of emerging discussion around sort of data-centric versus model-centric strategies?
Yeah, I think there are two parts to the answer. One part is based on the research that you're referring to. And like one notable paper in that space is the unreasonable effectiveness of data. Initially, it was done for the NLP domain for language models, and then it was reproduced multiple times for computer viz, for advanced language models based on BERT architecture, and so on. So essentially, having more data is better than having a more complex model, but there are things.
Well, is it more data, or is it more data, or more good quality data? I think that's the interesting bit.
That's basically the next step. But setting it aside for the moment, having more data beats more complex models, given all other things are equal. Now we start thinking not only about the technical part and like the research component of it, but the business side. And in that case, what I'm observing is that there are models out there, pre-trained models published as open source, and you could use very state-of-the-art architectures, the ones that are showing up at NIPS, at CVPR, and several other prominent conferences in the AI domain. And essentially, you don't modify the architecture of that particular neural network. You just search for the one which fits your business application, given the combination of speed of inference, throughput, data requirements, size of the model, and assessing those parameters. You say, oh, I think I need to use, let's say, ResNet 152, or I want to use like Mask RCNN, or I want to use YOLO because I have to do like fast processing of images in real time. And then you start thinking, oh, do I have enough my data to fine tune the existing open source network to work it good for my application? And the differentiation as a business actually comes from having that unique, clean data for your specific application, because everybody could fork an open source model, pre-trained model, but very few companies have that unique asset of having clean data. And that's, for example, what we do in our application. So obviously, we collected a lot of public data related to computer vision, and then we selected a subset related to, silency detection and semantic segmentation and so on. And then we found problems in those data. For example, MS Core data set that Microsoft released a while ago for semantic segmentation, it has limited resolution for our task. It has images like 600 up to 900 pixels in size. And in our application, where we work with high fidelity data that is coming from e-commerce, and we have to make images so sweet that people buy products online by looking at those images. So we have to work with HD. Because of that, even a pixel level mistake in annotation is crucial for us. And we started working with different agencies to feedback that cycle and get proprietary labeled images of full resolution that could help us fine-tune our models and differentiate from the competition and from open source. So that's basically how the actual world works.
Yeah. So it sounds to me like the data-centric side of things is very much where you live ultimately, because your bottleneck, regardless of the architecture that you manually, if you like, select based on a degree of your domain expertise, in the end, it's the quality of the data that's an issue for you in your application, right? And I guess I think this is kind of the thesis of some of those authors that have published those papers around data-centric versus model-centric, which is that in the end, optimizing the model, all you're doing is really trying to kind of deal with noise in the data post hoc. That's what you're trying to do. So in the end, that's why the data quality matters. But if we look to the other side of it, I'm interested, Rajdeep, because I know Microsoft is one of those companies that has the means for doing either deep model development or looking at advanced AutoML techniques. And when I think about advanced AutoML techniques, I'm talking about things like neural architecture search, the use of reinforcement learning for finding internal architecture for deep neural networks and things. And I know that Google recently released an open source project called Modelcentric that basically uses basic building blocks of known deep learning architectures to try and find optimal architectures for specific novel tasks. Can you kind of enlighten us a bit about perhaps what Microsoft is sort of looking at, perhaps with some of its partners like OpenAI, in terms of the ability to provide solutions that can self-optimize the model beyond the kind of traditional ways that most people would be familiar with?
No, absolutely, and that's a great question. So yes, we had been always a great proponent of democratizing AI, and we have done it in several ways, right from exposing the deep models that we had in terms of cognitive services that I spoke about, but we are doing a lot of research in terms of AutoML as well, in cases like classification and regression. And I myself use AutoML, and it's just awesome, right? So it can look through a space of models, and after that it helps in doing the hyperparameter tuning as well, to your point. But I guess there is another aspect to it which I also want to add here. So AutoML is real. It's part of Azure machine learning, and you can we try to expose everything as REST endpoints, and so that we are not bound to a platform or a specific language. You can use Python, Java, Scala, R, .NET to call these REST APIs and to use these automated machine learning capabilities. But added to that, complementing to that, I would say there are some other aspects where we are investing a lot of research, and that is on the interpretation of it, right? You talk about libraries like Interpretability that we heavily invest in partnership with Facebook, and this libraries essentially can interpret machine learning in a simple way. For example, what are the weightage of different parameters for both glass box model as well as black box models like neural network, and expose it to the business audience. So there are two parts to it, right? So one is, of course, AutoML, investing in AutoML so that we help the data scientists to quickly find, narrow down the scope of models that are going to get used, right? So that is there, but we are also investing on how to explain those models. And I can go a little bit deeper on that, how we talk about fair learn, but or fairness of that model, but maybe that's a different topic. But that's so we have huge amount of investment. And we are seeing a huge amount of traction on those capabilities, because guess what? As data scientists, they spend most of the time in data curation, which we talked about, getting good quality data and annotating good quality data. But right after that, I think the second place where the most amount of time is spent is on experimentation. And if we can automate some of it, or most of it, that will help the organizations to go and drive the business value faster.
Yeah, no, absolutely. And I think this bit about explainability is actually a real challenge when it comes to certain environments where we are obliged to pre-package training pipelines. For instance, in federated learning and federated learning environments, I think there's a real challenge there about the fact that we necessarily have to pre-package pipelines so that they can be deployed in those distributed environments, run their own training in a distributed way. But then how do we deal with the interpretability side when we're doing this kind of global aggregation back again? So I think that's a really interesting aspect that's kind of overlooked when we talk about pipelines and AutoML and so forth, and the interpretability, as much as I think that's now getting more attention in the community.
Yeah, for sure.
Yeah, so I think we can come back to the interpretability and explainability part in a bit, because I would like to touch back on that. But I just want to bring us then onto something I just mentioned, which is this concept of machine learning pipelines, because we've talked about the importance of data quality and what we might term sort of a data-centric strategy around machine learning development. We've also talked about the applicability of AutoML for the optimization of models. And I've just mentioned something that some people may have heard of called federated learning, which kind of necessitates the combining of those two things. Nick, from your perspective, just to kind of, again, go back to sort of basics for people, what's your understanding of a machine learning pipeline, if you could explain that?
So I would say, in my opinion, the difference between the model and the pipeline is one thing, like the former, the model is map the input to the predicted value, the target variable, but the pipeline is system level.
Oh, I'm afraid we're losing you there slightly, Nick. We seem to have a dodgy
thing. Sorry, there are some...
Sorry, Nick. Yeah, I think you just hung up slightly there. I think your connection dropped out on us for a moment. Do you mind just starting again for the audience with your explanation?
Yeah. Sure. So basically, as I said, there is a model, machine learning model, and then there is a machine learning pipeline. The model is just a set of coefficients, right, that define the mapping between the input, between the features of a new instance and the target variable. And this is like a very abstract mathematical object. But the machine learning pipeline, I would say it's already an engineering concept. It's a system level concept which defines how you ingest the data, how do you pre-process the data, then how do you actually push the data through your machine learning model, and then how do you serve it in a scalable way. So essentially, the entire chain of data processing that delivers end-to-end experience from data ingestion down to a specific prediction. And from that point of view, there are two types of pipelines, right? The training pipeline and the inference pipeline. The training pipeline obviously is necessary for creating a model, and it must maintain reproducibility property, such that once you have a model, given the same data, you could literally get the same model, which is statistically insignificant from the one that you had before. And this is very important for us to have very good governance of models over time. Otherwise, it just becomes a mess, because you just change one hyperparameter, drop a subset of your data set, and then you have a different model, and then nobody knows how to get the model that worked last week in production, right? So you have to have very good lineage of that part of your data pipeline, machine learning pipeline. And then the inference is essentially, how do you take already trained model, take a new piece of data, pass it through the entire processing mechanism of your backend, and then serve it in a scalable manner. And in that case, I would say the focus shifts to model maintenance, model monitoring, and essentially everything that happens after the model is put into production to interact with the real users.
Absolutely, that's a beautiful explanation. Thank you very much. And I think that this is one of the things that, particularly sort of more junior data scientists or business leaders that are kind of new to the field, kind of really need to be educated about, which is that training a model these days actually is relatively easy. It's not necessarily a big skill, and probably not the bottleneck anymore for scaling and returning effectively ROI on these systems. And it's actually really about these. Like you say, infrastructures that are really an engineering problem about how do we put these models into production. I think that one thing you touched on there that's really important for people to understand is about this concept of model performance, model drift, and data drift, right? That means that we need to have, as you described, this kind of special CI/CD for machine learning. Rajdeep, I know you come from a very strong engineering background, so you seem the obvious person to kind of get to explain all of this to people. Do you want to kind of explain a little bit about what I'm talking about there, MLOps and that management of models and drift?
Yeah, no, I think that's a great segue, right? So there are two distinct conversations here. One is about data ops, and other one is MLOps. The way I want to start all this is right now we are at a correct stage when organizations should think about implementing this practice, right? We are not in that Wild West stage where the data scientists and machine learning engineers or the data engineers can touch or could have touched a production system, and then human errors would crop in and run havoc, right? So we need to implement those touchless systems, to your point, implementing DevOps cycle where you work on your development environment, it automatically moves to QA, and then after certain automated tests and some quality gates, it should move to production. And then so that cycle has to be implemented, right? Now there are challenges to it. And Nick mentioned quite a bit of it. Now, there are challenges in terms of data preparation because we have multiple data sources, multiple formats, and then the cleansing and the transformation. Some of it we can use SMP systems. For some of them, we have to use distributed or MPP systems, right? On the model building side, the choice of algorithms is huge. We cannot restrict the data scientists in terms of choice of language or the development tools, right? So we need to support a variety of systems. Now, the model training side also gets interesting because there are code-first approach. For example, I like to code, but there are no-code and low-code approach as well. For example, as a machine learning designer, where you can drag and drop and create a training pipeline, and it works as well. And then there are distributed training. There are places where you actually have data sovereignty rules or data security for which you need to train these models in your on-premise. Although you are in cloud, but the model training or the data has to be on-premise. So that's there. Model registration and management, we talked a little bit about that. The versioning of the models, because version 1, version 2, version 3, and then suddenly version 3 is not working. We need to have an automated way to go back to version 2. And by the way, also say why we are going back from version 3 to version 2 to the business and to the legal, if it comes to that. The model repository, tracking the experimentations, very importantly, the containerization of the environment, right? Because as I said, the choice of environment and the choice of language and the libraries are enormous, right? And then last but not the least, your model deployment. So you have to deploy your model. You might have a real-time inferencing need. You might have a batch inferencing need. And guess what? We need to put monitoring on top of that as well. So it's a lot. And unfortunately, when we are thinking about MLOps process, we cannot just think about this entire thing as a piecemeal approach, that okay, we will do this and leave that. No, it has to be thought of it has to be thought as a end-to-end platform, right? Where the data engineering group is creating the data ops pipeline. The data is getting into a data lake, for example, or a SQL DB, and then your data scientists are training the model and experimenting iteratively and creating the ML models. And then they are registering the models, and the ML engineers are validating and deploying. And it's an end-to-end feedback loop. Some of the triggers that you mentioned, I mean, data drift, absolutely, it's a trigger, right? So you have a baseline of the data, and tomorrow, from the source, the data is getting changed. That can trigger a model retraining. And then model performance drift, it happens always, right? So the model, when we had put it in production, it is giving some performance number, and then over the time, if we are seeing it degrading, or guess what, improving too, that kind of raises a question, and then we can do automated trigger on that as well. And guess what? There has to be different gates, like cost, the compliance, the quota, because some of the models, so we talked a lot about the BERT and the NLP models, right? The deep learning models, they more often than not, they will be trained on GPUs, right? And GPUs are still expensive. As of today, they are still expensive. And so the cost plays a role, how often you are going to retrain those models, right? So, but the best part about this, I know I mentioned a lot of moving pieces and a lot of things. The best part about this is there has been a conscious effort from the commercial, the big commercial providers like Microsoft, Google, and even Amazon, on making this process more and more mainstream. So, for example, in Microsoft, we have a very, very standard MLOps process which integrates with Azure DevOps, and of course GitHub. We own GitHub also, so you can have a DevOps pipeline, or you can use GitHub Action and hook the machine learning and do this end-to-end process. And the best part is, at least from Microsoft's side, we're trying to make it very open. So you don't necessarily need to be on our platform to use the MLOps process. And I think that's what we need. We need more openness from the commercial vendors so that more and more people can actually use the standardized process and make the machine learning side of it work like a standard software deployment, so to say.
Yeah, no, absolutely, and we recognise that you guys are providing all of that, and the thing is, I think weirdly that the bottleneck for most people is actually the availability of engineers that are knowledgeable in MLOps and that are skilled in the DevOps skill set to actually build and configure these systems. And actually, it's one of the things that us at TDAB we recognise, because we build these a lot for our own customers. We're now building pre-configured, as you say, end-to-end, out-of-the-box solutions for customers to stand up very quickly, so that then they can just kind of get on with doing the creative or innovative parts in terms of the machine learning experimentation and so forth. Nick, from your point of view, it'd be cool to kind of illustrate the issue of, I think, data drift, because it's something that's so often misunderstood, particularly by sort of business leaders rather than the more technical people. Could you just kind of briefly explain the importance of drift monitoring and why it's important in terms of managing your model performance when you have models in production?
Yeah, sure. So essentially, what is a data drift, right? You have a distribution, and all machine learning methodology, deep learning methodology as a subclass of machine learning works only if you get data from the same distribution. If distribution changes, but you have the model trained on the previous replica of data or previous version of the distribution, then it will start making mistakes. And that leads to problems. Either it leads to, let's say, incorrect predictions, or it might harm users. They might have bad user experience, or the model might start discriminating people. And because of that, we have explainable AI, as a subfield, which is advocating for more interpretability in the AI model development. And essentially, you don't want to use the model that is outdated on the new replica of your data. Now, what are the challenges happening here? I like to draw this very famous diagram. I know, essentially it's square matrix, right? This is, on one axis, something what you know about the world, and then this is something that is available for the world at large, right? And you might know something like a subset of things, but there are things that you don't know, and you don't know what you don't know, right? So essentially, this is completely black swans that exist out there. And moving this analogy to the machine learning terminology, you have data. And your data is obviously not a universal set of all events happening in the world at the moment. It's a sample. And as any sample, it could be biased sample, right? And from that bias, you could have very different implications. You could have bias related to, let's say, some long tail cases, right? So for example, in applications, developing and saying what objects do you have on that image, right? It's very standard image tagging model. And then we built object detection model, which not only tags an image, but also draws a bounding box around an object and says, okay, this is a tiger, this is a chair, and so on. And then into production, it was great, but we built an application specifically for professional photographers who photograph animals. And then in that specific community, for some reason, they had portraits of animals in a photo. Not like the animal is photographed, but there is a poster of an animal sitting somewhere on the wall, and then this poster is photographed. So essentially an image in an image. And then we obviously said that it's a tiger, but it was not a tiger, it was a poster containing a tiger. And then our users told us, no, we don't want you to tag such images as tiger, this is a poster. And then we had to fix that, but it was a very tiny structural trick on the model, not understanding that the frame actually changes the concept. And this brings me to a very practical, very, I would say, under-discussed aspect of machine learning model evaluation. By now, many people know what is cross-validation and what is statistical model evaluation, right? You have a sample of your data, you take a subset of your data as a holdout, you train on 80% of your data, and then you evaluate it on the rest of 20%, which model haven't seen before during training. And it becomes a fair evaluation of your model quality on that sample. But again, you don't know what you don't know. What if in your sample you didn't have those images or very small representation of poster images, but in the real world, for that specific niche community, that could be a popular frequent case. Humans, some cases, and based on those edge cases, say what else must be put into the backlog to improve model quality. And then based on a specific edge case, you already start thinking, can we fix it using model fine-tuning, or we have to collect an additional very unique subset of data that covers a blind spot in our original sample. And that's what makes this really difficult. And that's what makes it very exciting at the same time.
Yeah, absolutely. I think this aspect around shortcut learning is, like you say, something that's often been overlooked. It's not taught in early ML and deep learning courses. I think there are some other really fun examples out there. I think actually it's at Microsoft. You guys, Rajdeep, often talk about a case that you guys had where you had an image classifier, and I think it was huskies and wolves, and what was found that was in the end the image classifier was learning simply on the fact that the wolf always had snow in the background, and then when it was presented with an image of a husky with some snow in the background, it was classifying as a wolf, but what it was learning was the snow, right? And I think there are some cool, Nick, I'm sure you know more about it than I do, but some cool methodologies now that in computer vision that have come out around using mapping of Shapley scores onto images, so you can actually understand visually on the image what's driving what parts of the image are driving the classification, which is, I think, very, very cool indeed. Okay, so that's I think that's really probably been very helpful for people to understand some of those concerns. And like I say, it's one of the things that I find with business leaders having to explain to people that machine learning algorithms are not firstly static things. As the world around them changes, they need retraining. It's a bit like having employees. You train them once. If you don't retrain them and keep them skilled up, their skills are going to be irrelevant for the world as the world changes around them. One final sort of question I want to kind of get to in the last sort of 5 minutes or so is just around then when we think about building models, pipelines within which we have models. These pipelines tend to address, and the models within tend to address quite narrow industry use cases, right? Like I think, Nick, you spoke about strong AI earlier, and of course the converse of that is weak AI, and very often machine learning is thought of as being weak AI applications. So how, firstly, Rajdeep, how should an organization that's thinking about building machine learning applications, how should they think about designing a pipeline for a specific industry use case, right? Like whether it was like customer churn, what are the kind of the considerations in designing that pipeline?
Great question. I think very relevant as well. Now, the thing is, impact from AI is not immune to the Pareto principle. So really 80% to 90% value will sit with 20% of the potential use cases, right? So the first thing that any industry really would or should do is to find those high value, low hanging use cases that are good candidates for machine learning. And I'm because I'm in Houston area, so of course I work very closely with the energy industry, but I would still try to take it from a generalized side of it, and it becomes industry specific whenever we are picking up a particular problem. But the good part is, even if we are talking about industry specific problems, the starting phase more or less is generalized, right? So for example, from a rigid and risk averse environment, the leaders need to look at a more agile, experimental, and adaptable environment, because guess what? It is not guaranteed. We have solid machine learning pieces on place. We have achieved human parity at so many different levels, computer vision, chatbots, and whatnot. But still, a perfect solution to your problem is not guaranteed. So it's experimental in nature. So that mind shift has to be there, especially in the traditional industries which are lagging a little bit behind on the adoption of machine learning, right? They have to also consider the build versus buy side of it, right? To your point, because even if they have identified a use case, they need either data science in-house or they need to go for a commercial offering to build it, right? And they have to think about the quality of the cost, the data quality, very important, right? For any industry, they need to look at the data, how they will annotate it, how much they can rely on a legacy data system. So patience is, of course, becomes a virtue, and then last but not the least, I think this is actually where they should start. Is the ethical implications of machine learning, right? Can they really interpret and explain the model behavior? Is there potential for the model being unfair? And this comes again and again in financial industries, for example. And then comes protecting the data, right? So they have to adhere to their industry level data protection guidelines, as well as the national or regional level data protection guidelines, right? So how they can protect the people and their data, like, for example, differential privacy and working with encrypted data using homomorphic encryption. This really cannot be an afterthought, right? Talking about any industry, really. So those are some of the points that comes to my mind.
Super stuff. Thanks very much. Nick, we're running slightly low on time, so I just wanted to kind of give you the chance to sort of, ad lib, if you like, any of your sort of last thoughts or pearls of wisdom for the audience when kind of considering this issue around machine learning pipelines and sort of data-centric machine learning. Kind of what are your sort of your last thoughts and recommendations that you have, or anything particularly exciting that you're seeing coming in the field that you would recommend people to look into?
So I would say it's important to think about that problem at the platform level, as Rajiv said earlier, and I could just second it one more time, that really you could build an isolated AI model for X, you could build a second, and then
oh, I think we've lost Nick there from it. Sorry Nick.
I have a spotty Wi-Fi for some.
Yeah, you cut off.
Yeah, so essentially you build. You build different isolated AI models for different isolated applications. Then, as an organization, you start losing a lot on the AI opportunity in general, if you think this way. Instead, it's much more important to start thinking about it at the platform level and start thinking about the building blocks that you could start reusing within your organization to enable more AI adoption over time. And I like to cite that statistics, so like graph shared publicly by Google. Back in 2015, obviously Google is AI first organization from the very beginning, right? The search algorithms, behind Google search, behind ads network, obviously built based on machine learning. But only in 2015 at Google, there were like very few machine learning, like real large scale machine learning applications. But the good thing that this graph was growing exponentially after that. And now it's like more than 1,000 different applications, according to that graph, inside Google, powered by ML. Every single decision which is made, there is some ML component inside of it. And the same happens for a new organization trying to transition to the AI first organization or adopt this new powerful technology as an enabling technology for their organization. And if there is no platform that could enable it at scale, then from one side, there is a huge demand after the first few successful applications of AI. On the other side, there is still very low maturity at the platform level. And this gap makes, as all people like to cite it, like 70 to 89, up to 90% of all digital transformation program fails, machine learning production models are not deployed, and so on. Why it happens? Because people start thinking about isolated applications and not systematically at the level of whole organization to balance supply and demand together.
I completely agree, and in fact, that's exactly what our experience at TDAB has taught us, and is what we're actually building now. Is that instead of we've come from a history of building lots of things bespoke for customers. Now, what we have is an out-the-box infrastructure platform on top of which we then build specific applications for the customers, precisely so that we take that foundation layer approach, and then, like you say, I think the really critical thing is to not look at these use cases in isolation. You want to find use cases that are complementary to each other. So, for instance, if we take like a manufacturer, you may want to do remaining useful life estimation to predict when a part will fail in a machine, but complementary to that would be to do anomaly detection so you can understand what in the machine is currently operating out of distribution. You can then connect onto that another pipeline that is effectively a reinforcement learning pipeline, so that we can have a pipeline that manages and optimizes for the risk of failure. And those things, as you scale them horizontally, actually then leads you from a weak AI singular application, for instance the remaining useful life side of things, to actually a system that, when horizontally scaled, starts to look much more strong AI like, right? That you can predict when something's going to happen, you know what's going wrong, you can self-optimize to minimize it. You could even have a front end with a conversational interface that allows the human engineer to converse with it. So I think you're totally right that approach to sort of modular design thinking of these whole system architectures is absolutely what people need to think about. Rajdeep, what about you? Just final thoughts. Perhaps you can put also a view for us about where big player like Microsoft is viewing the world is going. What can you tell us?
Right. No, I think I would like to conclude saying this, that we need to go beyond just improving the data and the models and the performance indicators, right? AI should be responsible, and it is really all about how we design, develop, and deploy these systems that are fair, reliable, safe, and trustworthy, right? And to do this, I think we need to think of responsible AI as a set of socio-technical problems. We need to think about the people who are ultimately going to be interacting with these systems. And at Microsoft, trust is at our DNA, right? Whatever we do, we do with trust and maintaining the privacy concerns. And I think for all the organizations, at whatever stage they are, responsible AI should be at the top of their mind. That's what I would like to conclude with.
Fantastic. Yeah, and I think me and Nick would probably totally echo that. And I think it's a segue myself into the end of the program. You spoke about privacy there, and for me, one of the most exciting things that is sort of that's emerged in the last couple of years is federated learning and the ability to train models locally to where people's private data is kept, and then just simply aggregate back results. But I know that that's a conversation for another show with Bright Talk, so I'll not go any further. I'll leave very much the conversation there. So I'd firstly just like to thank you both, Nick and Rajdeep, for your time and all your great insights. I'm sure the audience have really appreciated it. I want to thank the audience for attending this 16th episode of the Business Intelligence Report. And just remind everyone that if you click through the attachments button in your player, you'll be able to register for the November 24th episode of our series, where we'll be discussing a slightly different topic, which is SaaS BI for the modern workplace. Lastly, we'd obviously really appreciate your feedback on today's episodes and any suggestions for future topics that you would like to hear. We'd very much like to get your suggestions. So one last time, thank you very much, Nick and Rajdeep. Really enjoyed having you here in the conversation, and hopefully see everyone next time. Thank you very much.
Thank you. Thank you for having us.
Yeah, thanks for having us.
Thank you.
Cheers.
Cheers.